of our products. He's the video person. Okay, we also have the option of Zoom. I was expecting to have more people here, that's the idea. But in case somebody cannot make it, is injured or something, you can actually do it from home. So that's the idea. So, Sani, the floor is yours.
Thank you, David. So as David said, I have been here since late July, and I will be here for another 4 weeks. I'm an ELG036. If anybody would like to come by and chat, my door is always open. If the door is open, I'm inside. So please feel free to do so. So starting with sort of a look back. A look back at where we were and where we are. As most of you know, semiconductor technology has been going on for many years. We've progressed from, for example, something like the Intel 4004, which was the very first microprocessor that was built, which had 2,500 transistors, was built in 1971, and was in 10,000 nanometer technology. I'm using the new, because you guys don't know what microns are, because your life was in nanometer regime, not in micron regime. This is 10 microns, right? Yeah. On the other side is Apple's M2 chip, which was done last year, or this year, sorry. 20 billion devices, 5 nanometer technology. And you can sort of go down here, all the sort of exponential growth things that have happened over time, going from 10,000 to 5, roughly a factor of 2 to the 11 reduction in feature size, 2 to the 22, the square of that increase in density. Right? We've done this. We, all of us, and the people, and the giants on whose shoulders we stand, right? We did all of this. So, but what was the impact? So here's an idea, here's sort of a view of the semiconductor market size from 1987, so not quite going back as far as the previous slide, till last year. And if you look at this, it kind of looks like a triangle. So you do the multiplication, and it's roughly $10 trillion, right? So the area of this triangle. So the total amount of market movement of dollars, let's say, was 10 trillion. At the same time, you can also look at how much these semiconductor companies spend on R&D, right? Because if you're a company, normally you divide your expenditure between, cost of goods sold, marketing, etc. And of course, you have some R&D, and the interest, and this is across different parts of the world, the average of those is roughly 13%. So that tells you that you have $10 trillion times 13% money that was spent in just R&D to support silicon. You're late. Okay. It's nice to say that every now and then. So in fact, if you look at this number here, right, the 2021 R&D semiconductor impact. Oh, no, I'm not going to say it again. You're okay.
They really got scared.
So just to give you perspective, right? We all know, COP27 just finished and all that. We all know about global warming, and right? We all care deeply about these things. And yet, the amount of expenditure in silicon is 5 times that of what it is for energy. 5 times, right? So you would think that gas and oil and solar and wind is such a big industry. No, they're way smaller. So over this last 35 years, 1.3. Where's that? 1.3 trillion went into semiconductor R&D. And I wanted to point out this absolutely great book, which is with Nani right now. Mike, I just finished this. I had COVID a few weeks ago, and this was great COVID reading. Finished it in 4 days, I think, or something. This book quotes the history of semiconductors from the beginning until now, talking about all of these kinds of things. You know, the economic impact, the technological impact, the social impact, etc. If you have time, highly recommended reading. So we did all this, right? We spent 1.3 trillion, and what was the result? Well, look at that. We have a world full of technology that we built. By we, I mean double E's, computer scientists, physicists, chemists, etc. You know, your phones, your mobile networks, your cloud services, and even the hidden devices, things like your heart implant or stuff like that. And we've taught people, again, the engineers, we've taught people that those things just work. They just work. You know, you get your phone, you turn it on, it works. I mean, rarely it doesn't work, but usually it's something, you know, most of the time it works. No, sometimes it doesn't, but you know, we blame software, right? I think this is a picture I took when I was in London. You know, so one of the screens decided to blue screen on it. But the key thing is that what we did is we taught people to depend on these devices. So we depend on our phone. If you depend on the GPS on your phone to bring you here or whatever, right? So we value dependability. This is the information technology pyramid. You know, it starts at the bottom with the silicon. On top of the silicon, we build things like networking, storage, memory, processors, etc. And then on that, we build operating system software. This is a new layer, the virtualization. This didn't used to happen maybe 10 years ago, but nowadays everything is virtualized. And then you have applications in the internet, and up top is all the stuff you depend on, right? You depend on the directions from your phone. You depend on the texts and emails and WhatsApps and all that. Now, the funny part is that, you know, we normally think of infrastructure as being something big, you know, like, you know, the infrastructure of this building is 5 million pounds of concrete. This is the opposite. We have all of this stuff resting on this very modest, small thing. And of course, you know, when we look at these layers, we know that we have interfaces between them. And one of the key things that enables us to build such complex systems is that these interfaces between each of these layers, so, you know, from the silicon to the processor to the system, etc., that we hide the complexity of the systems by using abstraction. Abstraction is one of the key concepts that we have. So, you know, when you think about it, right, here's an Airbus A380. I looked it up. It has 4 million parts. 4 million parts. Sounds like a lot. But, you know, the M2 chip we talked about a minute ago, billions of transistors. Not only that, when you think about how we go from some detailed transistor to the chip that actually uses these transistors to implement some software, and then finally to the user experience, all of that happens because we're able to abstract at each level. When you're at this level, you know, the precise behavior of the electrons as they're crossing the channel, you don't even, it's gone. It's completely gone. Oh, this animation should not have happened. Never mind. Yes. So the most recent issue of Science last week had a very nice set of articles about the history of the transistor, 75 years. So starting from the beginning, and so again, recommended reading if you're interested in sort of this part of the world. So abstraction, right? We rely on abstraction to manage complexity. The other thing that we rely on, and that's quite unique to information technology and VLSI and design and all that, is the reliance on simulation. we don't prototype, right? You don't go and build a processor, check it out, and then decide, maybe you need to fix it, and then you don't do that. You simulate the processor, you show that the simulation works, you do any optimization, et cetera, and then you go make it. And of course, that's because we cannot afford prototyping. Making a chip is already a very, very complicated and expensive thing, right? So we have these very sophisticated simulators, right? You have some model for the environment in which the thing is operating. You have a model for the design itself, and you have all of these internals, with algorithms and numerical. And I promise I will not describe simulators in detail. You've all used them, right? Whether it's the circuit level or the logic level or the high, or even at the system level, right? We do that. We use that because we want to predict the behavior. And sometimes we forget to do that. There was an example recently of, they made this plane a while back, and it was a very fast plane. And the plane was so fast that it would go faster than the bullets coming out of the gun. So if you use the gun to shoot, you would even, I'm not kidding. So these guys, forgot to do the proper modeling of this one little thing. And so this plane actually is capable of shooting itself down. So that's why it's important to have good models. Now, so why do we have these simulations? We have these simulations in order to make predictions, right? So we have this thing that we showed before, and that's kind of like the design side. But then eventually, once we have the design finished, we go and fabricate it, we implement it, and then we look at the device that we made, we measure it, and then we do this model to hardware matching. This was one of those IBM-isms that I don't think many other companies use. Model to hardware matching, right? You have a model of how you built the hardware. You have a piece of hardware, you measure it, and then you match them together. And if they match, then you have confidence in your prediction. So abstraction, simulation, prediction. So I posit, in the beginning we said we wanted things to be dependable. And I posit that dependability means predictability, right? In order to have a system be dependable, you must be able to predict how it will behave. And once you know how to predict it, then of course you can go fix it if it doesn't do the right thing. So, for example, we can do if we have if we have made a processor and the processor maybe is not as predictable as you would like, you can always, for example, fix the behavior via frequency voltage scaling or any kinds of things like that. So in the rest of the talk, I'm going to take the simplest possible technology thing, for lack of a better word, and use it to drive, because David warned me against going too deep into that part. So we're looking at wires, right? The simplest part of a chip is a wire that connects 2 points. So in this graph down here, on the x-axis, we have the age of the wire, 1 second, 100 seconds, etc. And on the y-axis is the CDF of wire failure, right? So let's look at this, right? So if you have a wire that looks like this, right? So this wire, as it ages, is increasing its resistance because of, we're going to talk a little bit more about that later. But it starts at 0.01%, it goes up to 0.1%. It's a small change. You say, okay, I think of this wire as being reliable, predictable, simulatable, all of these good things. Now, if on the other hand, you had a wire that looked like this, where, within, let's say, a few hours, the wire went from, the wire probability failure went from 0.01 to 100, then that wire is pretty useless, right? You just turned on the chip and like 1 hour later, boom, right? So terrible wire. The problem is these in-between wires, right? So a wire that maybe has, 12 days, years, whatever. What do you do with that? How do you deal with this kind of phenomena? Even more, how do you deal with this kind of phenomena if it has some kind of variability around it at the higher levels of design? So the key idea here is a dependable system needs predictable components. And the predictable components can sometimes be not so nice in terms of their behavior, and therefore we need to be careful about them. So what has changed? Why am I talking about this? So until relatively recently, now I have to admit this is recently for me, and I've been doing this for many years. For you, maybe this is quite old, so excuse me. So 65 nanometer, right? This was kind of like the Marina, don't laugh at that. Until 65, you could kind of clearly see two kinds of types of failures: hard and soft. And don't ask me why they called them that. This is a terrible name, but that's what they called them, right? So hard failures are catastrophic, like that wire that went, burned up. Soft failures are usually like, oh, this chip maybe is a little too much leakage, so has a little bit too much power, blah, 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 blah. And when what you would do then is you would go into the fab and you would clean it up. So the first thing you do is you remove particulate contamination, you look at the individual processes, you make them cleaner meaning less likely to produce faults, and then that removes the catastrophic faults. And then you look at the tolerances, how much variability you have in your threshold voltages and etc. And then you tighten those and boom. So that was the recipe for how to make a fab profitable before 65. This is now no longer the case. It is now the distinction between hard and soft is a lot harder to deal with. So it's not possible to always assume the fab is going to fix it. And therefore, our systems are going to be less predictable and therefore less dependable. And therefore, we're going to need to deal with these things at the higher levels of abstraction. So in order to sort of to understand these soft and hard and all that, here let's just think of a circuit of some sort, right? So on the x-axis is resistance. Remember, again, I'm trying to make things simple, so I'm just looking at some wire resistance, right? So on the x-axis is resistance, and on the y-axis is the delay of the circuit. We all know that delay is important because it determines, the frequency and the correctness and etc. So you have some specification for the delay. You designed the circuit, you want it to run at a gigahertz or whatever, so you have a spec. Now, when the resistance has no increase in it, right, everything's fine, right? So your performance is better than the spec, everybody's happy. Now, as you start increasing the resistance, you get to a point A, where the performance of the circuit is at the spec, right? So if you keep going and don't do anything, the circuit will fail because the delay will be higher than what your specification is. So then you adapt, right? So you change maybe VDD, or you cool the chip, or you do something in order to keep it going. Then you get to point B. After point B, you have no choice. There's nothing else you can do. You've already, for example, maxed out VDD. If you make it any bigger, the devices will start burning up. And so you get degradation. And then finally, at point C, you get failure, right? The circuit doesn't work anymore. So, you can think of it like, here's, in this case, this is my nominal output. And it's delayed a little bit, but it's still within the spec. Here, it's delayed a lot more. And here, it's just not inverting at all, right? So this is an inverter. And this wire here is so high in resistance that it can never go low, right? So this C point that we're talking about there is indistinguishable from a Stackgate fault. So whether this resistance increased a lot or whether there was a defect here that prevented the contact is not distinguishable. And this might look quite exotic, but actually in SRAM, this has been present since even before 65 nanometers, that there will be cells in your array which will not hold a 1 or which will not hold a 0, meaning no matter what you do, that cell will always be 1 or 0 based purely because of the threshold voltage statistics. And just sort of to visualize, this is old data that I generated with a bunch of others at some time. So, looking at different technologies, looking at the sigma at which an SRAM fails, the sigma at which a simple latch fails, and then a sigma at which the inverter fails, right? So, oh God. Hi, nice for you to show up. Thank you. Is that?
That's a perfect arrival. It's exactly where you want to go.
Right. So you'll see that in SRAM, even in 45, we're working at like 3, 4 sigma kinds of numbers, right? Which is, remember, in SRAM you have millions of bits, so this is many bits failing, right? Now latches, in 45 you're at 10 plus sigma. It's like, who cares? Even, we do have a lot of latches in the design, but 10 sigma is many, many, many zeros. But look where the trend is. In 22, the latch had the same failure rate as an SRAM in 45 in this particular set of simulations. Inverters tend to be much more robust. It's a very, very simple circuit, and so you can ignore that. But the key point, yes?
Sani, are these actual technology nodes? Or
these are actual, these were actual technology nodes up to 16. The 12, this is IBM's. The 12 was extrapolated. Yeah. This work was done a long time ago. Yeah. You're making me feel old. Okay. So this is the only deep technology slide I will have, I promise. So why is this happening? Again, I'm sticking with wires, and I'm realizing that I'm in between you and your lunch, so I won't go too long. Here's what a wire looks like inside, right? Remember that most wires nowadays are made from copper, and copper has a crystalline structure, and so you end up with these grains inside. If you look deeply at a wire, it's not like some nice uniform thing. It's made of like clumps. And these different clumps have boundaries between them and stuff like that. And what happens is the electrons, as they're flowing through the copper, some of their energy is imparted to the copper atoms, right? I mean, why do we have resistance? Resistance happens because an electron hits the atom of the conductor. So we know it has to happen, right? So, but if all the electrons are going the same way, eventually those atoms will move because you keep hitting them and hitting, right? And that leads to electromigration and all this kind of stuff. The key thing here is the size of the grain boundaries has become comparable to the size of the wires. It used to be we had nice big wires. Who cares if there's grain boundaries? But now, the mean free path of electrons in copper is 40 nanometers. So now the structure of the wire and how it looks is on the same scale. So it's much harder to make those predictions. This is a picture of what will happen if you let it go. So the first part of this dependability thing is, how do we predict these failures? And of course, this means that you have to add models in your system to do all of the the details. And I've only looked at resistance, and there's a many other things that you have to consider. One of the things that we did at IBM is that as we started looking at this, is we realized there's a lot of stuff happening we don't understand. That we simply don't know X, whatever X is. I have an example here of something, right? So vias, vias are just the connection between two wires. You have a wire in the X direction, a wire in the Y direction. you connect them with a via. You all love vias, I'm sure. If not, you should. They're wonderful little things. So we went. The fab was telling us, oh, you know, I think this was at 32 or no 65. We're having, you know, there are issues with vias, you know, blah blah blah. What do we do? What do we do? You know, and so in my department, you know, we took it upon ourselves. And I understand that this is not something that is easy to do in a university setting, but at Intel or at TSMC or something, you definitely would be doing this kind of stuff. We made a test structure with different kinds of vias in it. And then we said, oh, well, let's just measure them, right? If you don't know something, make a test vehicle and measure it. And now at least you know something. And what we found out here is, for example, you know, here are via resistance distributions for two kinds of vias, right? This via is at the edge here. So it is sensitive to, you know, misalignment along both directions, lots of variability. This via is only sensitive to misalignment of the blue wire, less variability. And then if you put two vias, gosh, it's nothing at all. There's practically no variability. I mean, comparatively, it's very solid, right? So when you look at a PDK and it says you must use two vias, that's why. They know that. By the way, I once gave this talk. I think I was in MIT or something, and notice how like I don't have an access number here, because these are numbers that, you know, the technology guys in IBM did not want us really, you know, advertising these numbers. And then this kid in the back says, I know what your via resistance is. So I don't know if anybody here is clever enough, but he looked at just the relationship between these and he inferred what the via resistance was. Very clever fellow. So the second part of this is, okay, so let's say you do this kind of stuff that we did before, this test structure. So now you have an understanding of vias. Well, how do I incorporate uncertainty in that? And again, I'm going to go to wires, right? So here's fail time, and here's, you know, your product lifetime. So you want the wires to last at least this much. If you're Apple, then you make it 2 years because you want them to buy the next iPhone. If you're Samsung, you make it, I don't know, 6 months because their phones are terrible. No religious arguments. So, you know, if you look at this, you say, okay, here's a very nice, dependable wire, rock solid, small amount of uncertainty, I don't care. This wire has uncertainty. I mean, it's not constant, but it's so far from the fail time that I don't care. And here's a wire which fails rarely, not too often, but maybe enough that I should be concerned about that. And then, of course, finally, you have, you know, some absolutely terrible wire that's like you would not want to use that. So the goal here is that you want these lower level parts of the hierarchy, the circuit device level, to present these things to the higher levels. Why? Going back to our pyramid, right? What we want is we want some kind of contract at each of these levels, which doesn't just say what performance is going to be, but also tells you what the dependability is going to be, right? So we're familiar with the parts of this that are just like, oh, the circuit will go faster or the circuit will go slower. But we don't necessarily have as much abstractions or as much models to say, you know, at what point will this inverter fail? Not slow down, but fail, right? And what I'm trying to tell you here is that we're at the point in technology where this is becoming important and we have to consider it. And we have to consider it both at this level, you know, from the silicon to the fabric, you know, the fabric being a processor, memory, etc., and then from the fabric up to the software levels. Now, it's not like, you know, all these problems, it's not like, you know, they're being ignored, right? The technology guys, you know, they apply things like OPC at the 20 nanometer level, you know, various layout regularity, you know, like making sure that things are lined up and all that, double vias and all that. And then at the same time, there's been recent work about fabric level regularity. Most famously, I think from CMU, they came up with some ideas there. Didn't go very far, but I still think that has potential. And then, of course, you have chip adaptation. So there is stuff happening in the technology side to try to combat some of these effects. But it's not enough. And the leverage that you have at the system level is much, much higher than at, if you're trying to correct shapes at the bottom. So here's the stack up there, right? Layout, schematic, RTL, high level software. You can tell this was made by a person who works at the lower levels because the software is like, oh, software, right? So, we look at this and, here we've already done work at the bottom, right? So at the sort of schematic layout, there's all this kind of stuff you do where you say, okay, fine tune the circuit, size it, et cetera, et cetera. But what we want to do is to say, well, how do we link that up one level higher? Because the software guys need to be able to have at least an understanding of what a fault will be, when a fault will happen, how frequently, under what circumstances, et cetera. And so this cross-layer approach is needed. This is some work that I did with some friends in Germany from a DFG project where we sort of looked at this problem and we decided, okay, you know what, the fulcrum, the point between all the crap that happens at the bottom and all the sort of complexities at the top is a bit flip, right? Forgive me, analog guys, I don't care about you. So this is just digital. So in the digital world, right, what we care about is a bit flip. So we just need to, we can take those two worlds, right, the software level, system, operating system, etc., and then down at the bottom, all the silicon stuff, and we can say, okay, there's a point in between where we need to be able to predict a bit flip in a latch, a bit flip in a gate, a bit flip in an SRAM, whatever. And if we can just make, all of this stuff feed up to the bit flip, we can take it from there to the higher levels. So the challenge there now is like, okay, can you build models of the bit flip as a function of the technology stuff? And once you have such a model, how would you use it at the upper levels? So I'm actually done pretty much with my talk. I'm just going to go on back to sort of the Moore's law thing, and again, looking at a side issue that probably only the older people here care about, but funding. So in these early times, I'm calling it the golden era, right? This is when companies like Xerox and Bell Labs and IBM, there was a huge amount of money in dollars of that time being poured into silicon, right? And so, Xerox, right? I mean, some of you may not, they did more than copying machines, right? They did build really interesting computers and software. Same thing with Bell Labs, GE Research, etc. Right, so that kind of led to the proliferation era, right? At some point, we got the PC. Everybody has a computer now, And at that point, companies like Intel, TI, Microsoft, IBM, they controlled the agenda. And we continued scaling and all that. And here, mostly companies, in this stage, nations were investing in silicon. You would go and see, for example, what Taiwan did or Korea. Like the government was pouring money, not just some individual company. And then something strange happened, right? We got into this consolidation part where things became too expensive. A lot of the companies merged. Technology development became so expensive that many people couldn't do it. And so a lot of companies left that. And you sort of shifted the balance of power to companies like Google, Apple, TSMC, and etc. And at the same time, somehow the funding agencies were convinced silicon's gone. Yeah, where carbon nanotubes or carbon sheets or whatever, something else is going to be taking silicon. So investment in R&D really reduced quite a bit. So a lot of the universities, a lot of the professors, it was like all of a sudden, what used to be very big quantities became ever smaller. I think maybe a little bit less in Europe than in the United States, but definitely across the world. And then something funny happened, right? We had COVID, and all of a sudden, all these guys said, "Oh my God, silicon is important," and so out of the ashes, the silicon, and as you know, in the US they put a few hundred. 52 billion. I know the EU did the same thing here. So all of a sudden now silicon is interesting again, and money's being poured back and on all that. So that's good news. So what do we need to do to keep this going? So at least, for the next 10 years or, whatever. I have an agenda, So there's a lot of things to do. And, as I said, for a while, silicon was like, who wants to work in silicon? Now it's like, ooh, you're working in silicon, yeah. Because, so I believe that silicon careers still matter. And I believe that this link between the lower levels, all the technology crap that happens, and the sort of the upper levels, which is where like things like EcoCloud, I'm assuming, are working, these are going to really matter. And contrary to what many people in the sort of carbon nanotube world think, silicon will be the substrate. Okay, so the $1.3 trillion that we talked about a minute, in the beginning, right? You wouldn't waste that, right? I mean, if you were paying out of your own pocket to make a technology work, do you think that all of a sudden you'll say, no, I don't like it anymore, I'm going to go do this? No, you will do everything you can to keep that investment relevant. And that means that whatever you imagine doing, it's going to be on top of silicon. It's not going to be a completely different technology with a completely different process. It will be integrated. And of course, I mentioned the COVID thing. The hiccup really sort of gave people pause. And hopefully, now that all of these dollars are rolling back, your career will be as blossomed as people in my generation when we did this. So I'm going to close with this beautiful picture and just a comment that Van Gogh was a great abstractor, and I think he would have made a wonderful system designer. Okay, thank you.
Actually, one minute to start. When I saw your car and said they are reliable, I would have to argue.
That's a very good point. I mean, a lot of people talk about how, in the 70s, for example, if you had a car, the car was a very simple machine, right? And nowadays, there are so many computers and so many wires and networks and all that we've actually made the car a lot more complicated. And so fixing it on your own, I mean, you guys, you will never do that in your lifetime because your cars are too complicated to be fixed by your own.
But even if you try to do that and you see simple safety system like airbag, if it doesn't go off, it's a problem.
It's a problem.
If you have it once.
Yes, Baba.
Sani, great talk.
Thank you.
I think that, well, it was $50 billion investment, and then some of it also come in Europe. Much of that may be more defense inspired than actually the need of the industry. I'm not debating that silicon is here to stay, and this 1 trillion, your retirement, my retirement will definitely make it. But I think what's really interesting in the future is that the embedded computing community did co-design where you thought about these layers, simple layer circuit, system, software, but that's going to be the future of all silicon.
Yes.
At all levels,
Yes.
where now at Google we have 12 layers of software. And this requires a match made in heaven between not just computer science and EE, but programming language folks at the higher level, intermediate representation folks who've been building compilers for many generations. Now they're doing hierarchical IRs, closer to the domain and then closer to backend. And then the CAD tools and all this wonderful stuff that the CAD community developed to bring this co-design together everywhere. It should be co-designed everywhere.
Everywhere. I would agree. I want to pick on something you said towards the very beginning because it's very important. I mentioned this book, the Chip Wars thing, and all that, and Babak made a very good point. Some of what is happening now is driven by politics and fear, and that book goes extensively into the whole Western world versus China and what's happening. And I'm sure you've all seen the various items in the news about, trying to prevent technology from going to China and all that. And it's sad that that's happening because, it's as humanity, we should behave differently. But that is what's happening, unfortunately. So yes, but the other point, of course, is that getting all of these things to work together will most certainly require rethinking all of these things. Maybe even like have a C minus, like a C that does faults, or whatever, like bringing those lower level things all the way up to the level that a person who otherwise might be a system designer or something becomes aware of them. And of course, they cannot be aware of them raw. They have to be aware of them through the tools. The tools have to become aware, because no person is going to sit there with a mountain of assembly code and say, what if a fault happens here? What if a fault happens? It's impossible. So there will be automation necessary. Sir.
Maybe what say that 3D integration will always be the technology of the future. And actually, you see this problem of having, silicon, new materials, sensor chiplets, okay, and putting them together. But the key question is, who will make the money by doing smart packaging? And what's your opinion on that? Because I think that's the key of the problem.
I think that's an important point, and in fact, 3D in industry. Okay, so I remember in 2002 or somewhere around that time, we did the first 3D chip in IBM, right? And we did that chip, and at the time, they did a 4-layer chip, and it was purely an internal effort. We weren't publicly talking about it and all that, right? And then I think a few years after that, all of a sudden, people in academia started publishing papers about thermal flux and heating, and what is interesting about this is that I believe actually that industry is quite a ways ahead of where we think they are, right? So AMD already does the chiplet thing that you mentioned. All of Apple's chips are multi-layer, right? I think some of them are too, and I think the most recent one in the phone. So this stuff exists. It's just that what used to be, like, for example, between Xerox and IBM and GE and AT&T and academia, there used to be quite good links. But those things don't exist in the same way between Microsoft Labs and Google and Facebook in the traditional that you and I know from those days, right? So a lot of work happens in industry, and I don't know what I should call myself, we or I or they, it doesn't go to you guys, right? So yes, packaging is important, and packaging is going to be super important for places like, for example, for the same reason I just said, China. If you're restricted to using, for example, a 12 nanometer technology rather than a 5 or a 3, what are you going to do? Well, you're going to innovate in other fields. And one of the clear avenues of innovation is to go make multiple technology chips, meaning chips with different technologies, package them together, get the best of both worlds, and do what you want. And so that's going to happen. The part that I don't like about that is that it seems to happen in industry, but the link between what the industry needs in this area and what academia is doing doesn't seem to be as robust as it should be.
That actually happened in the consolidation era, where the government said, okay, we're done with this, and industry took over. That basically is where the link broke.
Yes,
Right?
yes, yes, that's a very good call, yes. So what student is going to ask? Now the professor's, oh, one of you has to ask a question. The student's like, oh my God, Arthur. How about a postdoc? You're still a student, right? No? Okay, postdocs. We're going from professors to postdocs, please.
So I feel like the point was mentioned that most of this money is going to defense budgets where reliability does matter. I don't feel that.
Where, I'm sorry, where what?
Where reliability, long-term reliability does matter.
Does or does not?
Does matter.
Does matter.
But in consumer electronics, one of the big drivers of silicon technology, I don't think there is such a big pressure of making eternal chips.
Babak, do you have a a pacemaker?
Not yet.
Do you have a pacemaker? Would you like your pacemaker to have like a 2-year? Yeah. Not everything is an iPhone.
Yeah,
There's a lot of things.
The maker does not have to be at the technology, maybe.
I don't know. Maybe you want it to be there.
Go on 3 gigahertz speed, and it can be made on more reliable technology.
What about if you wanted an implant in your eye to help you see? And that probably will require quite a bit of horsepower to process and give you stuff. I mean, we don't have it right now, but this could easily be something that the brain, the neural interfaces are just now starting to So yes, the simple things that we do right now around health and all that, your ECG does not require multiple gigahertz, but potentially, if you could, you could. I'm almost imagining like an implantable calculator. So I could actually calculate everything like this, right? I agree with you that maybe right now we don't necessarily have and you can even take it a step further and there are disposable electronics, not even, right? I mean, those silly cards that you open and they play music and what's that? That's going to be in 3 nanometer? No. So yes, there's always going to be multiple technology nodes with different price performance characteristics and all that, but I think for this dependability, this way in which what we do as a community drives society forward, drives healthcare is going to go through a massive rewrite in the next few years. The only thing that's stopping it is privacy. If all the hospitals in one nation could just put all their data together and then let you guys play with it and then make devices to handle it, we would be probably better off. But right now, the doctors are like, nope, I'm keeping this. I don't want to give it to you. They don't want to share it. They don't even want to share between themselves, between different hospitals. So, but once we get over that,
it will go faster in the US because hospitals are owned by chains.
Right.
Whereas in Europe, it's impossible.
But it's already happened in China.
In China, of course.
Yeah.
But I can also argue that even for more or less standard technology, you still want to have the newer technologies, but just simply reducing power. So you reduce voltage supply and so on, the system will consume. Don't make it go very fast. Want to make it last many more years. I know we are discussing here. So in general, even having a pacemaker is of course a problem, but you take an ECG sensor that you put, if it's tiny or it's a device like that you have it attached on you, you don't want to remember when to change the battery, so you can last for 3 months rather than 2 months. So we still use 3 nanometer, but a completely different spectrum. And you see, for example, Apple has a whole new design and discussion with TSMC, so it's a limited collaboration that we have unknown, where we are working on building this new type of technology, but for extremely new type of power. Planning to speak. And then negotiating together to do.
Yes.
Thank you very much for your I just wanted to comment on the previous question that actually on the reliability, you said that there is reliability is important, but you don't feel that there is a big trend. Actually, it depends on the system which you want to use. If it's the system like aircraft or the car or the health system, there are special standards which allow, which regulate how you build your electronics, the system, and what would be the level of reliability to be able to sell it. But if you want to do the computer level, this is the system which doesn't require that much reliability compared to the critical system. So that's why we want to spend less money, but you still can have the system with the acceptable level of reliability. And since we build mostly with the systems like computers, telephones, that maybe you would have experience. But once you go to aircraft,
or satellites, or you know, yeah. Cool. I have one last thing to show you. I have some thoughts. I put a slide. So when I first came here, that's the metro, that's a map, that's a picture, and I noticed that, I'm walking out of ELG and I'm going to the metro, and I was asking myself, how do I optimize my walking speed? And so I propose that, that what I'm optimizing is, the amount of time and the amount of energy, right? So I'm assuming that energy is proportional to the square of my speed, if I'm walking slowly versus, so V squared times the time that it takes me to walk. And then the time that I have, I walk for some time and then I wait at the metro for some time. And then alpha is just a proportionality thing because these are different units, so you have to sort of make some kind of Pareto between them. And so if you do that, and if you say, okay, I'm new, right? So this was my first day, right? I don't know what speed I should go at. Should I be running? Should I be walking? I don't know. So you can write, some minimization function. And then you realize that, well, the speed is just the distance divided by the time. And the expected value of the wait time is not really up to you. It's, the guys in the metro, right? They have some period. So it's a constant. And then you do all of that and you do the math and you set the derivative to 0. And this is the optimal speed at which you should walk, right? So whatever unit alpha is, take the square root. If you walk at that speed, you're optimizing things. Then after that, I said, okay, but what if I'm walking and I see the metro? Okay, so now this is a different problem, right? I'm walking, I've got to this point here, and I saw the metro. What do I do? So what should I do if I'm going to change my speed? And turns out that, if the first speed that you do here has to be square root of alpha, because you don't know if you're going to see the metro, right? And so you should stay with the optimum you already know. But once you've seen the metro, then you ask yourself, well, okay, I've walked this far. I saw the metro at t sub t. So my speed is alpha and a half. So the remaining distance is d, the length of this yellow line minus that. That's how far I have to go. Okay. Now he's gonna. So, but now you have to sort of guess how much longer do I have? And the only number that again, this is your first day, right? So you have no idea, is that time has to be greater than how long you've been walking, because you didn't see the metro here. So you went from here to here in t sub t, and during that time you did not see the metro, so the metro has to be at least later than that. So anyway, comes back to this equation. So if you do see the metro, then you should change your speed to be that. And I'm putting that out for you. can you think of other refinements to this model? Right? So for example, maybe there's a machine learning approach where you could say, well, this is the optimal velocity schedule. Or, maybe you say, I don't know what you're going to say. So
I found this on the web.
Alexa seems to have found something on the web. Okay. Well, thank you all for coming. My understanding is that lunch will be outside and my office door is open. I would love to meet you and to hear about your research and to help in any way I can.
Yeah, so you want to discuss this problem and others with Sani, please don't hesitate. He's available until the end of the year, so he will be actually with us. And we're already dealing with quite a few of the problems that we have in some of the labs. And he can have actually